you know, the Navy had reactors,
Yes.
and so the Air Force had to have reactors.
Very, very radical nuclear reactors, totally different than the kind of stuff we have now, based on the idea that you could take salts and that they would be a really good medium in which to have a nuclear reaction.
Well, we were young chemical engineers at the time. God smiles on young chemical engineers. They do things that in later years would be regarded as crazy.
It wasn't that I'd suddenly become converted to a belief in nuclear airplanes. That the purpose was unattainable, if not foolish, was not so important. A high-temperature reactor could be useful for other purposes, even if it never propelled an airplane.
This is an old facility. Look down before you walk. That's our biggest hazard here right now.
Oh my goodness. Yes, yes. I've modeled this shape neutronically.
It is like a lead pencil, isn't it?
Yeah, it is.
Basically.
Graphite.
We just returned from a trip to Oak Ridge National Laboratories, and one of the exciting things that the Baroness and I got to do was to tour the molten salt reactor experiment, which was one of these type of reactors that was built in the 1960s. It was an experiment that demonstrated many of the key technologies, although there are some that still remain to be demonstrated.
How long have you been here?
I've been here since 1992. There are very few people in mid-career in nuclear energy right now because there's a huge trough. We have a large number of students coming back into it.
Well, the context has changed completely, hasn't it?
It has. Yeah, when we went into nuclear energy, they said, "What are you, nuts?" There's no future in that.
And it really didn't matter. We say it's the true believers.
So you could have a molten salt reactor that you could walk around on.
Oh, this is so cool. You guys have got to try this.
Oh, goodness, that makes you feel really weird. There's something in front of me here, it feels like.
I was in 7th grade. I read an Isaac Asimov story about the implications of what free energy would do. And I sort of knew I wanted something, I was going to be an engineer or scientist just from day one. And this sort of said, okay, what can you do to make a difference? And that was where I sort of said advanced nuclear power was something that could make a difference, and that low cost clean energy could make a huge difference to society. If I'm going to have to get up every day for 50 or 60 years and working on something, well, it ought to be something I believe in. Liquid salts are an outstanding heat transfer media. It really doesn't matter what you're going to be transferring heat for, whether this be a solar power tower, whether this be a salt-cooled reactor, a molten salt reactor. Viscosity on it is 30 times larger, but water is very low viscosity, so it's still a very low viscosity fluid.
Some people might imagine this is quite a gloopy or kind of slow-moving liquid, but it's actually quite fluid.
You're right. It does go through a melt much like a glass as opposed to water, which doesn't quite do that. So we want to run it 100 C or so above this, so it does flow nicely. If you go ahead and you repeat doing things in here, you can see you start to etch the glass just a little bit. So what we have to do in a reactor is keep things very highly reducing. If you put extra beryllium in there, essentially giving you a preferred spot to rust.
And so this is all about controlling the potential corrosion of the salts within any vessel that you put it in.
Yep, the iron in some of the alloys is more soluble at higher temperatures, and so you will get your heat exchanger where it's at hot temperatures. You will get metals taken out of solution, and then it gets to the colder end, it'll redeposit, and so you can self-plug your heat exchangers, which you would very much like not to do. And your technique to avoid that is keep everything very well reduced so it doesn't corrode in the first place.
You'll make it lousy, but there are no strong chemical reactions that are going to take place between the salt and even direct contact with water.
The hazards on this, the same thing as hazards on a deep fat fryer, which is I trip. Throwing hot oil or hot salt in this case on visitors would be considered a bad thing. But there's nothing else to this, it just makes a nice little clear liquid. But I'll just pour this out into a little stainless steel crucible, and you could hear that little snap there was just, there was a little bit of moisture at the bottom of the stainless steel. I mean, at 450, I mean, this thing is a solid. So it doesn't take very long for it to form the solid again.
Isn't that a nice feature?
If you had a little crack on this and it was it was starting to weep, it forms a plug.
Self-plugging.
It's self-plug.
That's a nice thing, not being under pressure.
On the other hand, if your design keeps the vessel hot, it'll stay liquid on there, but that's why you have a guard vessel. If, you know, absolute worst case happens and you have massive vessel rupture, well, you still catch it.
The Navy program that led to the light water reactors we have now was well optimized to the needs of the Navy. It actually wasn't very well optimized to the needs of power production. The reason we have that as the base for our power reactor technology today is because the Navy was prepared to pay the first mover costs to make one work. And once you've done that, it's extraordinarily difficult to compete with it because those first mover costs are very, very high and have no financial return associated with them.
The Navy has built their nuclear submarines, and the Army has taken the same technology as the Navy, the water-cooled reactor, and they're doing their thing. But the Air Force wants to build a nuclear-powered bomber. Now, Weinberg was a practical man, and he said, nuclear-powered bomber. That is like probably a really, really, really dumb idea. You know.
Dirty little secret was that most of the people involved in it knew from the get-go that it really wasn't practical. In contrast to a submarine where you've got limited space, but you can shield it for the people on the submarine, it's much harder on an airplane because of the weight.
Most of us did not really think that the aircraft reactor really could work. But we did feel that there was a very interesting technology there that someday could be applied.
And I would maintain that Weinberg was absolutely right in his assessment of the situation back then. He knew that to make the nuclear airplane work, they couldn't use water-cooled reactors. They couldn't use high-pressure reactors. They couldn't use complicated solid-fuel reactors. They had to have something that was so slick, that was so safe, that was so simple, that operated at low pressure, high temperatures, had all the features you wanted in it. They didn't even know what it was. I think someday this will be looked at as one of the great pivot points of history, that if this program, this nuclear airplane program, had not been established, the molten salt reactor would have never been invented, because it is simply too radical, too different, too completely out of the ball field of everything else for it to be arrived at through an evolutionary development. It had to be forced into existence by requirements that were so difficult to achieve, and the nuclear airplane was that. So they began working on this high temperature reactor. And remember, this was invented before we had ICBMs or anything like this. This was a doomsday weapon. I mean, this was like, if you're flying this thing to Russia, it's the end of the world.
I suppose you'd have to say that it was a miracle that the homogeneous reactors operated at all, rather than that they operated well. Chemical stability of the system was not really sufficient. It was chemically unstable. The second reactor actually operated very well. That was the molten salt reactor experiment.
There it is. This is the place.
These things right over here are the spent probes. Those things would extend to like 60 foot in length. They went down the tank, did the melting, did this bubbling and stirring and everything. A lot of them, they started above the high bay.
When you say high bay,
It's taller and we can put cranes in because we can lift things up.
You had to go down an additional 25 to get to the top of the tanks. Then you had to go inside the tanks. So those things would extend. You got a pipe within a pipe.
The box is the top part of the probe. We had the controls. We could tell exactly how far down the probe was moving and the weight of it. And the probe had heaters on the end of it. Then it would melt a pool in that salt and would sink down in it.
So all those long-handled tools they had for operations, it was almost heroic actions, you'd say, when they were trying to do things. And you've got this length of distance, and we'd certainly try to design things today that could be robotically handled. It just would not be designed the same way as it was at that point.
One of the things that I've learned from talking to some of the old timers at Oak Ridge, I mean, these guys are in their 80s now, if they're even alive, people didn't disbelieve that we could build the machine. They didn't believe that we could maintain it.
Operation of the MSRE was not too difficult, and the people that I had working for me, they all had pound dogs under the porch, old cars out in the yard that didn't run very well. If anything came up side of the molten salt reactor, they said, "We'll fix that." "How you gonna do it?" "I don't know, but we'll fix it." And they did. One time, the sample capsule is down in the pump. Flexible steel cable got tangled up. We got bad news. Here's the end of that cable cut off. So I said, what are we going to do? And there's the good old boys for you. They said, isn't there such a thing as fiber optics? There's the capsule. And they fished that capsule out. We were back in business.
And they had a lot of long-handled tools, remote cameras. It was challenging, but he felt like, despite the challenge of operating high radiation fields, that they were able to operate and maintain that machine over the course of its lifetime.
We worked for several years on an experiment that proved that you can handle this molten salt reliably, and when things go wrong, we were able to fix. The advantages outweigh the difficulties, and the concept is ultimately going to be a practical application.
We still have a few folks who are even operators here who are around. Sid Ball's office is just literally 3 over from me. He was at the controls when it reached its highest power there.
He told me that was an accident.
It sure was.
Yeah, there's another way to tell that story too.
I was running some tests late at night. The device that I was using got stuck in the wrong place and pulled the rod out, and the power went up and up beyond the design power, and then controlled itself and went back down. Wow. Everybody was happy. I started out at the lab in 1957 and got onto the molten salt reactor project, the MSRE, molten salt reactor experiment, mainly in the instrumentation and controls aspects of it. But I quickly got into the dynamic analysis, which was a lot of fun for that reactor because it's an inherently safe reactor. The dynamics were, let's say, not common to reactors because it was molten salt instead of water-cooled solid fuel.
You could change the load on this radiator by moving the doors down, and the reactor would follow the load. I migrated to the MSR program doing the nuclear and mechanical analysis of the performance of the reactor.
Often folks are afraid that a reactor can run away on them, that a reactor is somehow an inherently unstable system that people have to always be keeping their eye on lest it get away.
Certain designs will be self-controlling. In other words, if the power tends to go up and the temperatures go up, it automatically corrects and shuts itself down, or at least doesn't let it keep going up.
And is it very hard to design a molten salt reactor to be self-controlling?
The nature of the molten salt reactor, the one with the fuel mixed in with the salt, is basically inherently safe and self-controlling.
Just about any molten salt concept that has been seriously considered has been shown to have this stable behavior.
If you have the molten salt in the core region and it heats up, it gets less dense, and that means it's less likely to go more critical. In other words, it gets less critical as the density...
Or less reactive.
Yeah, less reactive.
Yeah.
Well, I've been in this energy game for about 10 years now, and no one's ever told me there was a safer, more sustainable form of nuclear. So I was kind of instantly interested, and I kept thinking about it occasionally. I kept in touch with Kirk a little bit, and then Fukushima happened.
This is great. I mean, this is just what I wanted to have happen, is her talking to these guys and getting that straightened up. Oh man, it's just perfect.
Nick Engel's probably the most knowledgeable person around these days, right?
I've never met Sid. I've read all his papers. I've actually extracted all the text from him, converted it all, rebuilt. I mean, I don't know if there's anybody that studied his stuff more than me,
I've worked with him almost the whole time I've been here.
I was so tickled when I found out he was alive for the first thing.
I mean, how did you feel about the reactor now? I mean, it sounds like it was quite a boring job in a way, but did you feel fondly towards this reactor design?
Oh, yes.
It wasn't at all boring.
Well, I meant boring in the sense that, it was kind of safe. And
did exactly what we calculated it ought to do, and that's pretty satisfying.
Yeah.
The basic idea is thorium all by itself is not going to release nuclear energy. But if you hit thorium with a neutron, the thorium will absorb the neutron and it will turn from thorium-232 into thorium-233. It's going to decay into protactinium-233, and then it will decay over about a month to uranium-233. Uranium-233, if you hit it with a neutron, it will fission. In addition to releasing all that energy, it will release 2 or 3 additional neutrons. All right, so you need one of those neutrons to go find another thorium, and you need another one of those neutrons to find another uranium-233 to continue the reaction. You're fissioning uranium-233, but you're making a new one. But you can almost think about it as a pseudo-catalyst. If you had some uranium-233, you could catalyze the burning of thorium indefinitely. So through this process, you can essentially implement that very simple thorium cycle, and this is what Weinberg and his team were working on in the 1960s. The molten salt reactor experiment was the core. After they completed the molten salt reactor experiment, they went to the Atomic Energy Commission. They said, hey, gee, can we have some more money? We'd like to go now and build the real thing. We'd like to build the blanket, and we'd like to hook a power conversion system on and make electricity. They felt like they'd shot the moon. Well, the Atomic Energy Commission, unfortunately, did not share their zeal to continue with the technology.
Milton Shaw, who was the head of reactor development in Washington, called up Alvin Weinberg and says, stop that MSRE reactor experiment, fire everybody, just tell them to clear out their desk and go home, and send me the money for fast breeders. Milton Shaw was sold on the sodium-cooled fast breeder reactors, and I am not familiar with why that was.
The red line shows the expenditures on the liquid metal fast breeder reactor. And this graph only begins in 1968. At that point, the United States had already built several liquid metal fast breeder reactors. It's very hard to see the green line for the molten salt reactor technology. It's extremely low. And then ultimately, it was canceled.
We were competing with the fast breeder people at Argonne mainly. They just had more political sway than the molten salt reactor.
Do you see a prevailing opinion here about molten salt reactors?
We haven't been funded to look at molten salt reactors.
There's no opinions about
basic. The opinion is simple. Build IFR. That's it.
Okay, that's the opinion. Okay.
The problem with the MSRs is that they've never done it. They had one at Oak Ridge for a little while. Yeah. They went through and did a couple of little tests.
We realized that we were minor league money-wise compared to the other programs.
U-233 was tested here, and there was a little bit of U-235 in it, and they added some plutonium-239 in that fuel mix.
Do you know how much plutonium was added?
Oh, about 600-700 grams. They thought the U-233 was the utopia of uranium fuel.
Do you feel like the program had a sound technical basis, or do you feel like technical problems were the basis for cancellation?
Some of the technical reasoning that I heard for the cancellation was that there was a corrosion problem.
Tritium was raised as another issue. We made no effort on MSRE to do anything with tritium, and there was a perception that managing tritium was going to be a very difficult, if not insurmountable, issue.
This is the WASH 1222 report from the AEC. Did the people on the program feel like tritium was an insurmountable problem?
We recognized that tritium would have to be captured and sequestered for the system to be viable, but most people thought that that's something that we should be able to do.
Did the people on the program, particularly the chemists or the material scientists, feel that corrosion was an insurmountable problem on the program?
No. And in some of the subsequent work, subsequent to that initial shutdown, they did some experimental work that seemed to bode very favorably for an ability to solve that issue. As well as the tritium issue, by the way, because we did do some tritium experiments in that 1974 to 76 period, and those are documented.
Were either of you present when the molten salt reactor program was canceled in the early 70s?
Yeah, we were still working there.
Well, I was still working on the system. We were still finalizing reports on the performance of the MSRE.
I didn't see it coming.
Mr. President, since you missed our meeting on breeder reactor, we sent the message today, Craig. I told Ziegler to tell the press that it's a bipartisan effort. You know, this has got to be something we play very close to the vest. But I am being ruthless on one thing. Any activities that we possibly can should be placed in Southern California. So on the committee, every time you have a chance, needle them, say, where's this going to be? Let's push the California thing. You do that?
Nixon was from California. Hosmer was from Southern California. Chet Holofield, who ran the Joint Committee on Atomic Energy, was also from California. It doesn't lead me to believe that the president was seriously considering alternatives to the fast breeder reactor and other paths that could be taken. It was a focus on what can we do right now to get jobs.
The United States is going to go forward in building a breeder reactor. Now, don't ask me what a breeder reactor is. All of this business about breeder reactors and nuclear energy and the stuff is over my head. That was one of my poorest subjects, science, and I got through it, but I had to work too hard. I gave it up when I was about a sophomore.
Nixon, by his own admission, was not particularly well versed in the different types of breeder reactors.
Unless you're one of those PhDs, you won't understand it either. But what I do know is this, that here we have the potentiality of a whole new breakthrough in the development of power for peace.
Maybe it might have benefited our country a little more if Nixon had been able to ascertain the different values of different types of breeder reactors and why one might have an advantage over another. Representative Craig Hosmer, who was the fellow on the phone call that we heard earlier, said that if cost targets were missed, I, for one, don't intend to scream and holler about it. So it's not hard to see that they could see great economic benefits accruing to their area of the country. In that same month, the Atomic Energy Commission issued WASH 1222, which was an evaluation of Weinberg's molten salt reactor. It was highly critical of several technological issues that had been encountered during the development of that idea. More importantly, though, it almost completely ignored the safety and economic improvements possible through the use of the molten salt reactor technology.
This was the main focus of Oak Ridge for decades, and it was very abruptly cut off, and it was a very bitter pill to swallow for them. So a lot of these great minds, they thought their life work had kind of gone to waste.
The original shutdown came early in 1972 with a letter from Mr. Shaw that says, "Thou shalt stop right now." One anecdote that I heard, he said, put your hand on your desk, take everything that has to do with molten salt, sweep it off, and you're finished.
I saved all my documents.
I did too.
So you had this geographically isolated place with a huge body of concentrated molten salt knowledge that never got out.
We had a corpus of people in Oak Ridge who knew how to do this in the mid-1970s. They're literally dead and gone now.
People that worked on the molten salt reactor worked that, would come back and then they get shut back down. They come back and they get shut down. A lot of people got burned out from that pattern.
I've met a handful of them. They're in their 80s. They're not going to do this anymore.
What's happened to Paul Habenich and Beecher Briggs and those guys? Have you kept track of them, do you know?
Well, Beecher's been dead for a long time.
How about Paul?
Paul, I have not had any contact with him, so I don't know. Quite a few of them are dead now.
Well, that's true too, yeah.
You don't get taught this stuff in nuclear engineering school. I said one time in an online talk, you could get a PhD in nuclear engineering and never learn about this stuff. I got an email a few weeks ago from this guy. It was really funny. And he said, Kurt, I just saw your talk. I want you to know I just graduated from Purdue with my PhD in nuclear engineering. And I want to tell you, you're absolutely right. I have never heard of this stuff before. And he goes, I want to tell you, it's even worse than that because he goes, I'm totally a student of nuclear history and I've never heard of this. How did I not hear this? He goes, it's great though. He goes, you're absolutely right. This is top-notch stuff they did and we should be working on it right now. But it's absolutely possible for you to go through a normal curriculum and never learn about this.
This one time, thick books, spiral bound, and they're just jumbled all over this pallet. And I just reached down and picked up two of these big thick books, and at that time the workman came in who was going to cart it away. And my friend Yuri Gatt asked, what are you going to do with these books? And the guy says, burn them. You can have the 2 in your hand, but the rest have to be burned. What Oak Ridge was doing was taking all the technical manuals. They took up space, and they were taking about 1 or 2 of each. They were putting it in this library called the Central Facility. They were in Oak Ridge where you just couldn't wander in. The average researcher couldn't go in and see it, let alone did they even know it existed.
I've actually looked at Weinberg's papers. His papers are stored at the Oak Ridge Children's Museum in a walk-in closet. And you walk in and there's literally filing cabinets stacked to the ceiling. And nobody has gone through them, cataloged them, indexed them.
At one time, this whole courtyard would have been full of thousands of specimens that we could do all kinds of research and testing on.
Right.
He said, but one day, nickel alloys were at a real premium, like unheard of recycle value. And he said someone made the decision to come in. He said they cleaned out all of our lab specimens for recycle scrap rates. And he said it probably set us back a decade on some of our ability to roll out quick changes to our recipes.
Oak Ridge made a lot of these salt loops. It's where basically little circular loops of plumbing pipe where they would circulate this hot molten salt to see did it corrode the piping. And they would run these things for 20 and more thousand hours of operation. They were valuable artifacts of the molten salt age. Well, Oak Ridge was throwing them away. And Yuri Gatt was like, no, we need these if and when we restart molten salt.
We are trying to demonstrate some of the core technologies you have to make liquid salts a standard heat transfer material.
The idea of this loop to retain our expertise in using high temperature salts, to provide a platform for us to test different components, different reactor concepts.
Above about 600 C, it becomes technologically very difficult to transfer heat effectively.
The loop is designed to run at 700 Celsius. That's about 1300 degrees Fahrenheit. And the whole loop is made out of Inconel 600. Ideally for salts, you'd use an alloy like Hastelloy-N. Right now you can't really get the right components, the right shapes using Hastelloy-N, so we use Inconel 600. It's maybe not the best option, but it's the economical and available option. This one does flow, so as the salt flows through it, it sends a sound wave through, and that measures the Doppler shift.
Nice.
So these are fluidic diodes. It's a way to control a liquid flow without using like a valve. In normal operation, it goes this way, it comes in this side and out this side, and that creates a lot of resistance. It spins around and comes out. During an accident, the flow reverses and goes this way, and there's not a lot of resistance going from here, just flowing out here, because it doesn't spin around. Then there's a heat exchanger. That's another part of the test.
Is all the heat localized on the pipes, or do you heat the whole box?
Yeah, all the heating is in the pipes, well, either in the pipes or on the outside of the pipes. It's trace heated. You can see like coils of heating tape. All the pipes will be insulated with about 4 inches of insulation. There will be a crucible here. That's where we'll initially load the salt, pass hydrogen fluoride and hydrogen through it, and that will clean out the oxides and the different contaminants inside the salt. So once the salt's clean, we'll pump it into the storage tank. The salt is allowed to freeze inside of it. So that's an issue with salts where you can't have it just freezing inside of pipes, it expands, breaks. And the idea is we're testing a reactor concept where the fuel would be inside these pebbles, and we'll fill it up about this much, 600 spheres will be inside of it, and that's where the fission and the heat's created, and you got flowing flibe over it.
Can I ask what the theory was around using a sort of a solid fuel pebble into the flibe rather than dissolving the actinide into the salts?
Currently in this country, we're not really looking at the molten salt fueled systems.
Using a molten salt as a so-called working fluid, it is doing the job of transferring heat from one place to another. Molten salts have what's called a heat capacity, right? It's the ability to hold on to heat. They're great at it. In the example of your car, you want to move the heat away from your engine as efficiently as possible and then just disperse that heat. Boiling point of water is only 100 Celsius. It's only 212 Fahrenheit. Don't ever open your radiator. Why? Because it's under enormous pressure.
This building is the size it is, and it's the way it is, precisely to accommodate this event. They've designed this reactor so if this happens, all the steam is captured in this building and doesn't get out. It's much, much, much bigger than the reactor, and that's all driven by that 1,000 to 1 difference in the density between steam and liquid water.
The boiling point of a molten salt, however, could be 1,000 Fahrenheit, could be 1,500 Fahrenheit, depending on the type of molten salt. They do it at 1 atmosphere of pressure.
Visiting the potential coolants, water is the one most commonly used. It operates at relatively low temperatures and very high pressures. That's exactly what we don't want. We want to operate at low pressures and at high temperatures in order to achieve high thermal efficiency. Gas can operate at high temperatures, but it has to go to high pressure. Only the salts appear to offer the potential to go to the high temperatures and at the low pressures. And that's a unique combination.
Using a molten salt as a working fluid to move heat around is excellent. Because in the example of a molten salt as a working fluid in this case, you want as much of that heat as possible.
Now, fluoride salts can also contain nuclear fuels like thorium and uranium, and that eliminates a major cost of what we do today in nuclear, which is to fabricate nuclear fuels. Okay, let me talk about today's nuclear fuel. They take these fuel pellets and they slide them down these zirconium tubes, segregate the pellets along the length of the fuel assembly according to enrichment. They'll put the most enriched ones in the middle, and then they'll kind of decrease the enrichment along the length of the fuel assemblies. It's a ceramic. It's a lot like the stuff your coffee cups or your cooking ware is made out of. Great at going to high temperature, but not thermally conductive, and so it gets very hot along the center line of the fuel. I mean, this stuff has about the cross-section of a pencil, but between the center and the edge will be like 1,000 degrees of temperature difference. That puts enormous thermal stress on the material itself. You can't even come close to 100% burn. I mean, not even approaching it. If it gets too damaged, it's going to breach the cladding. It's going to let some of its fission products out. So you get very, very, very poor fuel utilization. And then if you remember when you went camping and you built a fire, it burns the hottest in the middle, and then the stuff on the edge isn't getting burned very good. They'll load in about 1/3 new fresh fuel, and then they'll reshuffle the fuel that's already been in there. They'll move it kind of from the center out to the periphery. All their money now is coming off fuel supply contracts. That's how GE and Westinghouse make money on nuclear power today. They don't build reactors, they sell fuel. Come along and say, hey, guess what? I got a reactor. It's got no fuel fabrication to it.
Making a fluoride salt, by and large, is trivial. Making a carefully enriched solid oxide is not. It is not.
So you could get an aqueous fuel.
In this system, in this particular,
you wouldn't put fuel in it.
There must be some advantages to doing the solid fuel.
If you want to use the salt as a coolant, it's just much, much, much easier to do something that's non-radioactive on this. So that's why we have the walk before you fly. The U.S. is electing to go after a salt-cooled reactor at first. Our method of rejecting heat is into the coolant. What we have are planks, about 25 millimeters thick.
You could put whatever kind of test you can imagine in this area.
We could put a solid plated fuel in. That test section can be replaced and others can be put in.
So if you're looking down from the top, there are 18 fuel assemblies arranged in a hexagonal grid.
In a solid system, you can't get into the bulk of the solid fuel. In a liquid system, you effectively have infinite surface area.
It is not to say that the U.S. doesn't recognize that molten salt reactors have some very interesting, advantageous capabilities, but they are a more technically challenging thing to do.
What is easier? Running a liquid past a solid in order to transfer the heat, or having the fuel be a liquid and use that in and of itself? So I would argue that actually combining the two is easier. Sure, it's more chemistry, but so what? I'm a chemist. There are lots and lots of chemists, on the planet. And a lot of them are a hell of a lot smarter than I am. So, go solve the problem.
It uses a fluoride salt as a primary coolant. It uses coated particle ceramic fuel. That's the triso fuel. This is the triso. Essentially, these are small kernels. They're smaller than a millimeter. We've got the fuel in the middle, and you've got a multi-layer structure, which is essentially, the important thing is the silicon carbide in here, which is actually a gas-tight containment.
Silicon carbide, even though we're using that as part of the design, That's part of the test. We're going to find out how that performs in a salt environment now.
We'll be doing natural circulation, safety testing, corrosion specimens in here in a pumped loop. Figure the next decade we will continue to use this as a base for our system. And you just happen to hit the timing such that the induction power supply is out being serviced, the pump is out being serviced here. We're expecting by the end of September to have the loop pretty well ready to heat up.
They're not doing neutronic stand-ins the way China is. So what's the freaking holdup? They got the last guy in the world who knows how to make these different kinds of salts. We're not asking for our national lab to do miracles. We're asking them to basically replicate something they did, you know, in 1952 probably.
Things went very fast in the 40s and 50s, not only because of the regulatory environment, but also because they were not developing commercial nuclear power. They're developing it. Just get a reactor up, show that it works, do experiments. Nuclear technology is well beyond that now. It's commercial production technology, and so you have to do things differently than we did back then.
If you wanted to just do an experiment, yes, you know, we can compress the scale and we could have something running at very short periods of time, but that's not what we're looking for now. We're looking to be a preferred source for energy for the nation, and that takes the more time.
Back when they were developing the molten salt reactor, they had numerous loops that were not fueled. These range from natural circulation test loops, from material testing to pump systems like this.
Most of the technologies that for a molten salt reactor as far as the thermohydraulics, well, they're identical.
So they're all very relevant, yeah.
There are a number of technologies that have never been done before in salt. That rotating flange up there with gasketed seals, the fact that we've got ceramic and metal pieces in a single loop.
Tons of stuff you're doing with FHR is in common with what we're...
I can certainly see that there are reasons for looking at thorium reactors as a follow-on and the true molten salt reactor.
You have your conventional solid fuel with a liquid coolant, you know, a fixed fuel form with a liquid flowing by it. Your pebble bed is a little bit of a transition in that the pebbles can kind of percolate up through, so you get some movement of the fuel. Then your next step is a slurry where you've got smaller particulate moving with the flow. And then the final step is actually just the fuel in solution.
You can almost imagine a continuum, but the pebbles just getting small until finally they're in solution.
So each of these are steps towards a full solution.
Different reactor concepts that we're actually debating internally within the nuclear lab system. Do we want to actually build a prototype reactor that actually demonstrates some game-changing technology for nuclear?
Yes, you do.
Right. But it's going to be a major national commitment when you're talking those types of numbers, and in that there's nowhere near that level of consensus that this is the right path to take forward. And without building that level of consensus, we're going to stay an interesting technology option for forever. We will never go beyond that.
We're funded through literally thousands of projects that come down from DOE and other government agencies where they say, we need you to go do this, we need you to go do that, and there's no line in the federal budget that says Oak Ridge National Lab, $1.65 billion, go do good things.
So we need something now to add to our grid with clean nuclear power that's going to get us to these advanced designs. And that relies heavily on the light water established technology that was light water reactor.
But it seems to be quite odd because it implies there's some sort of inherent process that we're going through that was dictated from on high. But actually all of those timings are just a function of how much money and resource you put into each element.
We live in a regulatory environment where you have to do in situ testing of things.
Creep testing for materials takes a fixed period of time. You put more money at it, you can't compress the time for long-term creep testing. The NRC, you mentioned NRC license requirement, that takes a set number of years to get that done. You can't put more money on that and get that done any faster than that. So you do reach a point where you just can't, push it any harder.
Now there are other parts of it that are absolutely resource limited, and you could go at more aggressively. And
we do the best we can with the resources that are available.
But there are people up there who control the resources. They're not going to make it happen, but they can at least ease the path.
It is shifting people's thinking to think a little bit more long term. Right now, there's a lot of focus on assuring the LWR industry gets, as we talk about the life extension.
Consortium for the Advanced Simulation of Light Water Reactors, CASTLE, It's an effort to develop high-fidelity integrated models of operating reactors.
We're focusing on pressurized water reactors, new fuels that are more tolerant and resistant to accident scenarios like loss of coolant and cladding integrity.
Right, so you're modeling a physical system. So how do you know this is right?
So these white areas are control rod guide tubes. And the center of one of these is called an instrument tube, and they can run a fission detector down that instrument tube and get an axial power distribution. So we can compare that.
Could you talk a little bit about the versatility of this with regards to other reactor types, particularly like MSRs?
You've got to worry about a different type of coolant and different geometries, but you still have neutrons, you still have heat transfer, you still have structural mechanics and all that base technology.
Then in fact by DOE said you must select and model physical reactors, show that it's relevant to actual operating reactors, not a design that isn't operating yet.
But in general, the simulation technology we're putting together we expect it to be broadly applicable to a large class of reactors.
This calculation here is looking at a fuel pellet that might have a chip in it, and what would happen is that you operate with a chip in a fuel pellet, what would happen to the cladding and the stress on the cladding. This actually shows what holds the fuel rod steady. If you get a gap in here, the rod can vibrate and wear a hole.
For the nuclear industry, for the most part, I think it's fair to say they're really not interested in novel concepts. They have problems today that they want some help with.
Some of the people that we were visiting with in Oak Ridge over the last few days were retirees who had actually worked on the molten salt reactor program. An issue that was repeatedly brought up was it's a very, very different kind of machine than what the nuclear industry is used to.
Suddenly here were these young people who were kind of showing an interest in their technology that they obviously had a real fondness for. There's now a whole bunch of people out on the internet that are following this, taking such an interest in their sort of pet project that they clearly loved. One of them said, "Oh, everything I worked on got cancelled." It's like, which they feel, that perhaps that their secret had been overlooked. But I think we're hopefully resurrecting it just in time.
A filmmaker in Canada put out a request on Kickstarter, which is a way to raise funds over the internet, saying, "I'd like to make a video. I've done everything up to this point for about $1,000. I'd like to get $20,000." When we told those molten salt reactor retirees that 600 people had donated $40,000 on the internet to make a video about their work, I can't even tell you how excited they were.
Yeah, it was awesome.
One of them looked at each other and they said, "This sounds crazy, doesn't it?" And he was like, "Yes, I'm not sure these guys are telling me the truth." Do you think building molten salt reactors in the future would be a good idea?
Oh, heavens, yes.
Dick, what do you think?
I think it would be a very good idea.
The people at the lab and other places around the country that study the global warming situation say that it is a serious problem down the road. How far down the road, I don't expect to see myself because I'm an old codger, but I think my grandchildren are going to see a heck of a big problem. Power reactors don't contribute CO2 to the atmosphere, and so they should, by golly, be pursued, period. And not to do it is sort of insane, really.
Even if you say that we can still go up into the polar regions and drill under very difficult conditions without disastrous after effects or side effects, and bring that out, we still have a finite source of fossil fuel materials.
Thorium resources are known to be very plentiful, and I think it certainly makes a lot of sense that India is going that way, looking at use of thorium as a fertile material, and I think we should also be looking at that.
Well, unlike most people, gentlemen, you two did something about it a long time ago, and thank you very much. I greatly appreciate all your work. Thank you, and thank you for your time too.
And thanks for dinner.
Exact same thoughts for me. Thanks for all your work.
Thank you.
You're very welcome.